Hi, we're going to look at some examples of finding limits from equations. So in some previous videos we thought about finding limits from graphs, but now we're going to look at some from equations, function equations. Alright, so there are a few examples here, and then the next video has a few more examples. For these first three, examples 2, 3, and 4, you might notice that that's the same function, f of x equals 1 over x minus 2, and we're just going to think about finding that limit from the right, from the left, and then question 4 is the two-sided limit. So questions 2 and 3 will help us answer question 4. Alright, so the first thing you might notice is that you cannot use a substitution shortcut theorem here to substitute in 2 because you would get 0 on the bottom of the fraction. So that is one of the ones you cannot use a substitution shortcut theorem for. So instead, let's think about what happens when I substitute in values for x that are just a little bit bigger than 2. So notice on this first one we're approaching 2 from the right, and so I'm going to be substituting in values that are just a little bit bigger than 2, and I'm just going to focus for a minute on the part of the function where x is. So I'm not going to worry about the rest of whatever's there, 1 over or a logarithm or trig function or anything else. I'm just going to focus on the part where the x is, and I'm going to think about that. Alright, so when x is just slightly bigger than 2, and then I subtract 2 from that, that part that I circled there is going to be approaching 0, but it's going to be approaching 0 from above. So it's going to be on the positive side of 0. It won't equal 0 because I'm not substituting in x equals 2, but it'll be just a little bit bigger than 0. And so that's important to notice that that denominator there is not going to be equal to 0, but it's going to be very close to 0, and it's going to be positive. Alright, so then when I think about the algebra of infinity that we talked about in the last video, one of the things that we talked about is that if the denominator is approaching 0, it's important to pay attention to which side of 0 that is. Alright, so when I think about taking 1 over a number that is very, very close to 0 but positive. So for example, you can use sort of some numerical things to think about it. If you take 1 over 0.00000001 and think about that. And so if you don't know what that is, you can try it on your calculator and see. But you're going to get 1 with 7 zeros behind it. Alright, so that's a big number. So that denominator is approaching 0 but positive, but that means that that overall expression is going to approach infinity. Alright, so I've written a lot of kind of messy notation here just explaining what's happening here, but let me just go ahead and write out here to the side using better notation. The limit as x approaches 2 from the right of 1 over x minus 2 is equal to positive infinity. Alright, and I just justified that by thinking through the algebra of infinity, indicating that the denominator is approaching 0 from the positive side, and then 1 over that would be positive infinity. That's enough. I can think about that numerically. You could make a table of values, plugging in numbers that are closer and closer to 2, but on the positive side of 2, and see what the function output is. You could also think about that graphically. I'm going to go ahead and draw the graph of the function here. F of x equals 1 over x minus 2 is just the basic reciprocal function, but shifted 2 units to the right. If you just think about that shifting function stuff that you did in pre-calculus and we reviewed at the beginning of this semester. So there's the graph of that function, which might be helpful as well. I'm going to talk about this really from the algebra of infinity, but remember that numerical and graph would always be a good way to sort of check your understanding and make sure that whatever you've written down makes sense. Okay, next one is the same function, but the denominator is going to be negative. In this case, we are approaching 2 from below, so we'll be plugging in numbers like 1.9, 1.99, if you want to think about that numerically. But the denominator will be approaching 0, but it will be on the negative side of 0. So when I have 1 over a negative number, that's going to make that overall expression get large in size, but negative in direction. So the overall limit on this one is negative infinity. And you can see that from the graph over here. As you approach 2 from the left, the outputs of the function are headed toward negative infinity. All right, and so that helps us answer example 4 here. This limit does not exist. And sometimes students say it does not exist because you cannot substitute in x equals 2, but that's not true. That's not what this is even asking about. The reason this limit does not exist is because the two-sided limits are different. Okay, so there are a few others here, and notice one of these is a one-sided limit. Problem 5 here is a one-sided limit, but 6 and 7 are two-sided limits. So just like problem 4 here, we were asked about the one-sided limits before we answered question 4, but even if they don't ask you that, then often you will need to think about those two-sided limits. So when we do questions 6 and 7, we will need to think about that as two-sided limits. All right, for number 5, it's similar to the function that we were working with before, but we just have a different numerator. All right, so I'm going to think about substituting in values of x that are slightly bigger than 2. So this denominator will be approaching 0 from the positive side. The denominator will be positive, but close to 0. And then when I take negative 10 over that, I'm going to get a number that's large in size, but because of the negative in front of the 10, I'm going to be getting negative values. So this limit is equal to negative infinity. And a good way to verify that that answer makes sense is to use a table or a graph of the function and look at those output values just to the right of x equals 2. All right, for these next two, we're going to need to look at the one-sided limits. So I'm just going to go over here and write those down. Okay, so I'm going to be thinking about, first of all, it doesn't matter which one you do first, but first of all, I've written down that we're going to approach 2 from the right, so numbers slightly bigger than 2. And so we have sort of the same denominator that we had before, but it's inside this square. So when I think about the x minus 2, that's going to be approaching 0 from the right, and then I'm going to square that, so that's going to make that denominator stay close to 0, but positive. So the entire denominator will also be approaching 0 from the right, and then 1 over that, that will make the outputs of the overall function approach positive infinity. Okay, for the other side, as I approach 2 from the left, so I'll have values that are slightly less than 2. So the expression inside the square here will be approaching 0 from below. So those will be close to 0 but negative values. But then when I square it, I will get values that are close to 0 but positive. And so that means that the limits of the overall function here will be approaching also positive infinity. So the issue here is that I've got that square that will make the outputs of the function always positive. So on this one, because the two-sided limits are the same, we would say that this limit is positive infinity. All right, number 7. Again, I need to think about the two one-sided limits. Okay, so when I'm evaluating this function at values that are slightly larger than 2, this expression inside the absolute value is going to approach 0 but be just a little bit bigger than 0. And then the absolute values won't do anything since the expression inside there is positive anyway. They won't change anything. And then at this point, now is when you want to think about some ideas related to composition of functions. So if you think about the natural logarithm function, when the inside part, or the argument of the natural logarithm function, so I'm thinking about the whole overall function now, but I'm thinking about the natural logarithm function when the argument, or the inside of the natural logarithm function, approaches 0 from the right. So I'm going back and thinking about my basic function graphs, and if you think about the graph of the natural logarithm function, has a vertical asymptote at x equals 0 and heads down forever, and so that limit is negative infinity. All right, and then when I think about x approaching 2 from the left, so I'll be plugging in values that are just slightly less than 2. So the expression inside here will be approaching 0 from below, so I'll have values slightly less than 0. But then the absolute value of that will make that positive. So that argument of the logarithm here is going to be approaching 0 from the positive side. And again, I'm thinking about the graph of the natural logarithm function when the stuff inside it approaches 0 from the positive side. And so I'm really thinking about this same graph, even though if you graph the overall function, ln of the absolute value of x minus 2, it wouldn't look exactly like this, but I'm just thinking about composition ideas. If I know the inside is approaching 0 from the positive side, then I can just think about my basic logarithm function graph. And so that is also approaching negative infinity. And so this limit here is approaching negative infinity. And again, this would be good to check with a graph or a table of values just to think about what that limit is. All right, next video has some more examples.